Today we are going to say Tikhonov's theorem for uniqueness. This theorem says that that heat equation, okay, when the heat equation has the initial data 0, okay, so then the continuous solution would be 0 only, okay. I mean, under certain mild condition, okay. So let us see this theorem. Why do you call such theorem uniqueness? Because this basically says that if I have one particular initial data, whatever it is, and then I cannot have two different solutions of the heat equation with the similar data, same data. Why is it so? Because imagine for the time being, okay, so let if possible that there are two different solutions u and v of the same heat equation with the same initial data, then u minus v would also satisfy the same equation because this equation is linear. So if u and v are both are solutions, then u minus v would also be solution. But in the initial data, they would nullify each other. So we are going to get 0 there. U minus v would be 0 in the initial line. What is my initial line? Initial line is actually time is equal to 0 and space is throughout whole. Okay, so then this theorem would suggest that this u minus v, which is solution of the heat equation and which has 0 value in the initial line, so that u minus v must be 0, okay, in the whole space. So that would also in other ways say that u and v must be equal to each other. Okay, so this type of theorem actually asserts or assures uniqueness of the solution. There are certain specifications which are very important. This is very important part to actually be careful. Okay, first we start with what do we mean by a C12. Okay, like I told that, okay, I'm looking for solution which is continuous and which is smooth there. So the general definition goes this way, in that I would say that if given function f is in C alpha to the power in the superscript C alpha of g semicolon r, if f is a map from G to R such that the map this f is alphath time differentiable. Now what is alphath time? Basically alpha could be multi-index, correct, because this m need not be 1. F need not be defined on one-dimensional space, but it could be a subset of a multi-dimensional space. There are actually m number of variables. So this alpha is multi-index, correct? Okay, so the alpha could be actually 1, 2 if m is equal to 2. That means that, okay, it is once continuously differentiable with the first variable and twice continuously differentiable with respect to the second variable if alpha is the multi-index 1, 2 and m is equal to 2. Okay, so in general, when alpha is just a multi-index, okay, and d alpha f exists inside the interior of the domain G, so G interior, this circle denotes interior, and has continuous extension to the part of del G. The del G is basically boundary. We denote boundary by del G. Okay, so continuous extension of del G, okay, which is in G. That is that if the boundary is inside the consideration of G, where f is given, I mean, if f is not defined on some point, we cannot talk about continuity of f at that point, right? We cannot talk about. However, if f is defined on some point of G, which is actually boundary of G, then we have the opportunity to cross verify whether f is continuous at that point or not. So how are we going to do that? We are going to say that, okay, that f is inside the interior, it is defined and it is alpha times differentiable, and that is continuously extended. So if you extend that means you take limit and the limit would coincide with the value of f at that point on the boundary, then we are going to say that, okay, f is continuously extended to the boundary. Okay, so if that is the case, then we call that f is in C alpha GR. So that is a notation. Okay. Now, if we look at this class of functions C1, 2, here alpha is 1, 2, C1, 2 open 0 closed T cross R semicolon R. Okay, so if you look at this and ask that what is it doing, so here boundary that capital T. Okay, so this capital T cross R, okay, capital T singleton cross R would be the boundary of this which is inside the domain. Okay, of course it has another boundary which is not inside the domain, namely singleton 0 cross R, which is not inside the domain. Okay, so this was just a definition of this notation, or what do we mean by this notation C12 functions. Sometimes, for such type of heat equation, it is pretty clear that what is first variable, what is second variable. I mean, generally it is understood that the first variable is time and second variable is space. So when we say C12, we mean that, okay, it is once differentiable with respect to time and twice differentiable with respect to space. I mean, this much regularity we need for classical solution of this equation, because here equation involves the partial derivatives of the first order in T and second order in X. Okay, now we ask that okay, so what is the solution of this which satisfies the following two conditions. Okay, first condition is that the limit of the solution, okay, I mean if you extend to the another boundary which is not included in the domain, say here T is going to 0 and Y is going to some X. Okay, so this way actually this I mean, a boundary point 0 comma x is the limit point of such points, correct? And we are asking that we are putting this condition that limit of u is equal to 0. Okay, so basically it is saying that although u is not defined on the boundary, because here the domain does not include the initial time, correct? It does not include. However, as we are looking at this equation, we are looking for a solution which is defined on this, and the solution, if you now approach to the initial data, initial value, that means approach the T goes to 0 and y is going to some x, then that value should be 0. Okay, so this is the way to put initial condition for a problem where actually 0 is excluded from the domain of definition of the function. Okay, and then second point is that we also require that u has some bound on its growth. Okay, that growth is e to the power ax square, so it has some upper bound of the growth which is independent of t, correct? So supremum over all t between 0 to capital T. Okay, if you take all these supremum, then this whole thing becomes a function of x, and we are requiring that this function is dominated by k times e to the power ax square. We understand that e to the power ax square grows very fast, right? Because it is exponential growth. Okay, but we are requiring that this is lower than that. Okay, we are going to see that why do we need this latter, but now for the time being we consider a problem which is like this, that you solve the heat equation, it has this initial condition and it has this growth property. Okay, in that case, okay, if you satisfy all these things, that case we can assert that u is basically the 0 function, the trivial solution, correct? Because if you put 0, so it solves trivially. If u is equal to 0, it solves trivially. So it says that u is the only possibility is the trivial solution. U is 0 on the whole space. Okay, so that is the Tikhonov's uniqueness theorem, and we call this theorem uniqueness because this theorem helps us to establish uniqueness of heat equation with general initial condition. Next, we see the proof. Okay, the proof is not too long, however, it has many steps, so we go through that slowly. So what is the goal? The goal is to show that the solution is 0 at every point inside the domain also, like so in the interior also. So to do that, we have to pick a point there, that means a particular t comma x we have to pick up, correct? Okay, so we pick up a x, okay, some x, we take some real number, and then so here for this exposure, for this proof, I am taking only one dimensional case. Okay, so here we consider x is in R. Although if you look at yes, so here also here all these things, I mean, although this definition was for multidimensional case, but here we are taking space is only one dimensional. Okay, now we given that particular x, I need to show that u of t comma x is actually 0. Okay, for that, there are many steps. The first step what we do is that we choose one integer n large enough so that n is more than mod x. Okay, x could be negative also, right? Positive, negative, whatever, but mod x is positive number. So choose n is n such that it is more than mod x. Then we define Rn, r subscript n, which is defined as minimum of Tn and minus and t minus n, where Tn is actually the heating time to the level of n. That means when Brownian motion which has started from 0, which become as large as n. Okay, so that is Tn, and T minus n is that when it first time hits minus n. Okay, so this is definition. T subscript y is infimum of t, that is first time when Wt becomes y. Now then this Rn, we know that at time Rn the Brownian motion value would be either n or minus n, and we also know that before Rn the Brownian motion value would be, the mod of Wt would be less than n for sure, for all the time. So that is going to give me some kind of control over the growth of the Brownian motion, and Rn is surely a random time. Now we fix some small t in close 0 to open capital T. I mean, that is as expected, as we have already decided, because we are going to fix x and t. Okay, so with this fixed x and t, then we define v of s comma x. So this function is defined as u of capital T minus small t minus s comma x for all s in close 0 to capital T minus small t. So what we are doing is that we have fixed t, of course, we have fixed x, of course, but now we are defining a function v on the interval close 0 to open capital T minus small t, so that when small s is 0 here, then I am going to get u of capital T minus t. When s is equal to the end point capital T, I mean, is approaching to capital T minus small t, then this would approach to 0. Although u of 0 is not defined, but this this variable argument would go to 0. Okay, so now given this is the definition of the function v, we can find out the partial derivative of v and write down the derivative in terms of the partial derivative with respect to u. So del v del s, here since the minus sign is there, would be minus del t of u. Okay, these two are equal of capital T minus small t minus s comma x. Now the other derivatives like space derivative of v is same as space derivative of u. So we are going to get del v del s plus half del 2 v del x2 is equal to 0. Earlier what we had with respect to u, for u we had del u del s is equal to del 2 half del 2 u del x2. Okay, so del u del t is equal to half del 2 u del x2 we had. Now we got sign changed, so we get del v del s plus half del 2 v del x2 is equal to 0. Okay, this is the new equation for v. When I write down del u del t, I don't mean that I am differentiating with this t. I am saying I am differentiating u with respect to the first variable. So this is an important thing to understand, that this notation del t u or del u del t does not matter what is my argument. It is first evaluated, that means when u as a function, you find out the partial derivative of u, this is the first variable, and whatever the function you obtain, you evaluate that function at the value t minus small t minus s comma x. Okay, it's chain rule. So it is like the del v del s is equal to the first derivative of u, this is first variable, times, then you write down del t by del s. Okay, so the first variable, how this this input is depending with this to s. but it is depending negatively, so you are going to get -1 sign, so that is here. And you would also get other terms like the second partial derivative of u, this is second variable, and how second variable is dependent on s variable, it does not depend, so multiple is 0, so only this would survive. There is also another way to find, see, is that the chain rule? Okay, so hence using Ito's rule, we are going to, so here there are some steps, since I have spent lots of time in Ito's rule, so I can expect that you will be able to follow. So let me explain. V of S minimum Rn, W S minimum Rn given W0 is equal to x. So this function, okay, this function, now a V is evaluated at some random time and also with some stochastic process. Now we are going to use Ito's rule for this, and if you do Ito's rule for this, we get that it would be V of 0x plus integration of V, partial derivative of V, and then integration with this W with appropriate the time limit. The integration, the limit of the integration should be appropriately chosen. This is Rn would appear, and then the second order derivative of V with the half multiplied, and the quadratic variation of W would also appear with the same limit of integrations. Okay, and then when you do expectation, okay, that stochastic integration part goes to 0. Actually, that we have proved as a theorem in 2-3 lectures before, and we have shown that okay, this thing can be written as expectation of V of S minimum Rn, W S minimum Rn given W0 is equal to x. Okay, so let us recollect that here what we were using here, that expectation of V of this random variable, okay, this thing is equal to V of 0 comma x. There basically we are using one theorem which we have already proved in detail in earlier lectures, that is expectation of f of w tau is equal to f of x plus this integration. Okay, and here you have the partial derivative of first order, here you have partial derivative of second order, and for our case f is not only function of the space but also function of the time, so that is not a big deal. Okay, so therefore you have also a partial derivative of f with respect to time, okay, and then partial derivative of this. Okay, and the way f is chosen in that case, that is V, such that the partial derivative of V plus with respect to t, del V del t plus half del 2V del x2 is 0. So this part would give you 0 there. Okay, so this would give you 0 there. So what would remain is that only that 0x, only this term would remain. Okay, and this part would be 0. Okay, because of the choice of f here, f is V here, and for V we have already obtained that partial derivative of V with respect to s plus half also appears here, correct? So half appears here and the second derivative appears here. Okay, and here this yt we are going to choose for our purpose the simplest one, that where u is 0 and v is 1, correct? So all these just 1, etc., and is one dimensional, right? So only half multiplied with the partial derivative, second order partial derivative of f with respect to space x would appear here. So we are directly using the theorem to conclude that v of 0 comma x is equal to expectation of v of s minimum Rn comma w of s minimum Rn given w0 is equal to x. This is true for all s between 0 to capital T minus small t, and also we have this is also not necessary to write down, but still we should keep it, that n is more than mod x, because we have chosen one x, okay, and x we are not moving anywhere, and we have chosen n is more than mod x. That is important in the sense that, so that this Rn, okay, etc., the time, so when you start time 0, your Rn is not 0, because if x is more than n, then already you are outside the domain. Okay, so we chose that, we chose n such that it is more than mod x. Now what we do, we are just, it is the matter of rewriting. So S minimum Rn, what does it mean? That when S is less than Rn, then it is S. So when S is between 0 to Rn, then it is exactly S minimum Rn is S. So Ws minimum Rn is Ws. When S is more than Rn, this is indicator function. So then this part will be 1. Okay, and then S minimum Rn is nothing but Rn. Okay, it's just rewriting of the earlier expectation. Now this is going to help us because this is the addition of two terms. So here what we use, that this v function from above, because v is actually obtained using u, and u is a solution satisfying the condition 3, condition 2, which is saying that, which put some growth condition on u. So v also inherits that growth condition. So mod v is less than or equal to k times e to the power of a n square. Why n square? Because doesn't matter, even if w is, s is very large time, but w, even if w exceeds the n minus n, but this would become 0, and this would become remain non-zero only when w is between minus n to n, and then I can use this growth property. That means this is less than or equals to k times e to the power a w square. W square should have written, but ws, when it is less than n, then only this part is non-trivial. For that I can replace that by n square. This is even larger, is also upper bound. Okay, so we got some upper bound which is deterministic, not random. Okay, that is good part of it. So I can say that, okay, this is like a bounded random variable. Now as s is now approaching to capital T minus small t, so here we are not changing n is fixed. Okay, so it's not n tends to infinity we are doing, but we are taking s tends to capital T minus small t. Why are we doing that? Because if s tends to capital T minus small t, then this thing argument goes to 0, and that is our goal. Why? Because we have information when u of this variable goes to 0. Okay, so that information we want to use now. Okay, and we can do only if s goes to capital T minus small t. So till now we have used condition 2, okay, here, but condition 1 we are now going to use. So as s approaches to capital T minus small t, then v approaches to 0 from condition 1. Okay, so this converges to 0 almost surely. And so now this modulus, here modulus is missing. Okay, so v of Rn comma Wrn instead of s, ws, etc. I can talk about this. Okay, this s should be here. Okay, so what does it say? It is saying that if s is more than Rn, okay, then only this is non-zero. Okay, but for those occasions, here this Brownian motion is not moving anyway, so it is at Wrn. Okay, it is not depending on s. Here it was depending on s, but here it is not. So this thing is v of Rn comma Wrn. Okay, but what is the value of Wrn? It is precisely either n or minus n. So I can again use the growth property that this whole modulus is less than or equals to, yeah. So there is a ambiguity about notation. Here I have started using capital K, whereas I think I was using, I was using small k here. Okay, actually both capital K and small k are same. Okay, for this slide. Okay, now, so as I was telling that we have now bounded and this thing, correct? So bounded random variable here. So since we have bounded random variable, we can use the bounded convergence theorem. So how are we using here? Because we are now changing s here, s going to capital T minus small t, and we know that v converges to 0 there. So u of capital T minus small t comma x, which was v of 0 comma x is u capital T minus small t comma x, correct? So already we have that. So left hand side I am writing just here, and right hand side I have this thing. Okay, but S appears here, and now I am letting S tends to 0, the capital T minus small t. So we are going to get this limit would come inside. So here VRN WRN one indicator. So earlier I had closed Rn comma infinity, but when I'm going to take S tends to capital T minus small t, that means from below to up, then the limit of that would be indicator function of open Rn to infinity of t minus small t. Okay, so I have explained it here, so I would explain this. Why do we get it? But first let me finish this reading this line. So V of Rn comma WRN, okay, this does not depend on S, so this does not change. However, this function surely changes because S becomes capital T minus small t. Only thing is that this domain also changes here, and given W0 is equal to X, okay. So for all, now this also we want to remind ourselves that, okay, our N was chosen which is more than N is actually strictly greater than mod X. Okay, so now here the explanation comes. If we have indicator function of, say, okay, there is also, so my A and 0 is the same, okay. So basically I should have written A here, okay. Indicator function of closed interval A B evaluated at point C, and then you are taking limit C tends to X. So what should be its limit? It should be A. Yeah, it should be A. If X is outside of the closed interval AB, that X is, say, less than A, then C is also less than A. So indicator function of AB at C would be 0, and it is 0 for all C which is less than X. So when you take limit C tends to X, this would be 0. So you are going to get 0 here. However, if X is inside the interval A comma B, okay, then I mean, of course you would get that sum. So then when C is less than X, that means C is less than A, okay. X is between A and B, open AB. So X is an interior point. So X has a neighborhood which is strictly inside AB. So when you approach X from the left, then you would enter the interval AB before, and this would become 1, and the limit would be 1. Okay, so here only thing is that when X is equal to A, okay, so that I have not written. So here I should have written less than or equal to A, because whenever X is equal to A, then also from the left if you approach, all the values will be 0, so the limit would also be 0. Okay, so there is a typo here. Okay, so this part is okay. So then that would give me that this limit function is 1, or indicator function of open A closed B. So applying the same rule here, so we are going to get the limit here would be open Rn infinity. Okay, now for every fixed t, okay, so we are now considering u of capital T minus small t comma x. Actually we have started considering from earlier slide, but now we have the details about this expression. So we are using this expression. Now this is upper bounded by this k times e to the n square. So we are going to use that. So we are using this, that this is less than or equal to k times e to the power n square times the probability. So because replacing the function by the upper bound, then from that expectation value we are going to get the probability that this Rn is less than capital T minus small t. Okay, and I'm just I keep on writing n is more than mod x. Okay, so this is k times e to the power n square probability that, so in other words, so just it is just writing the same thing in explicit manner. So when the Brownian motion starts at point x, then you are constructing this Rn as Tn minimum T minus n. But if you start from 0, then you have to translate it. So then it is the Tn minus x is less than capital T minus small t, and probability that Tn plus x is less than capital T minus small t. So both the sides, correct? So either n minus x or n plus x. Okay, so you are going to get these two addition of these two probabilities. So this is less than or equal to k times e to the a n square times probability Tn minus x is less than capital T given W0 is equal to 0. Okay, how are you getting this? Because this part is less than capital T minus small t. Okay, so this is smaller than this, so I've replaced this number by a bigger, larger number. So this has larger scope. Okay, so the probability is not smaller, so I can get this inequality. And probability Tn plus x is less than capital T here also for the same reason. Now here we explain that this is the, this involves some calculation, some estimates. As Ty is less than small t, that this probability is equal to 2 times. So this is this result is obtained from reflection principle, that Ty is less than small t. What does it mean? That before time t, the Brown motion hits y. Okay, so that probability is same as that 2 times, so the probability that Wt is more than y. Okay, so at time t, because it does not say that, okay, before time t Brown motion hits y, that does not say precisely that at time t it will be more than y or not. It could be lower, but it will be above or lower with equal probabilities. So from that consideration, there is a actually theorem which is called reflection principle that has this formula, the calculation based on this very simple argument what I told, that okay, it has half of probability going up and down, that to show that okay, it is equal to 2 times probability that Wt is greater than y. And now this probability is very easy to compute. Why? Because Wt is nothing but a normal random variable with mean 0 and variance t. I'm just trying to find out these values. 1 minus the CDF, correct? So this is 2 times y to infinity 1 over square root 2 pi t e to the power minus z square by 2 t dz. Now this whole thing, that I can write down in a little more simpler manner using some change of variable. Okay, so here we get y by square root of t infinity e to the minus z square by 2 dz. Okay, so this 1 over square root t we can get rid of. Okay, and then what we do, we actually take modulus of u. Again we go back to that same quantity u capital T minus small tx, because that is the thing we want to show, that it is basically 0, correct? Okay, so u of capital T minus small tx mod, so that is less than or equals to k times e to the a n square times. So here these probabilities we are now writing down. We are now using this, that this probability is we are writing square root of 2 by pi. Okay, so here we are writing instead of y, because n minus x we should consider now, because it's t n minus x, correct? N minus x. So n minus x, so divided by square root t, and here n plus a square root of t. So those two probabilities are now having this type of expressions, and then we are using this estimate also. We are going to use it because now it is in terms of integration, but this integration do not have any closed form expression. This is basically error function, correct? It can be written in terms of error function, but it doesn't have any closed form expression. However, we have this estimate that e to the minus z square by 2 dz integration from y to infinity is less than or equal to 1 over y e to the minus y square by 2. Okay, so one can understand, okay, cross verify in many different ways. One can actually so like y tends to infinity, this part would be 0, here also this part is 0, and one can actually do these calculations. It would involve some gamma integral, okay, but one can get this expression. Okay, So we are just using this estimate for replacing this integral term in terms of just exponential term. So we have obtained that mod of u of capital T minus small t comma x, this left hand side, is less than or equal to k times e to the power a n square, square root of 2 by pi, and then this integration is replaced by 1 over of this thing, correct? So 1 over of these things means the square root of t by n minus x, square root of t by n minus x, e to the power of the square of this term, so n minus x square by 2t. And similarly here we have square, I mean instead of minuses we have plus 6 here, so we have this term. Okay, and we should not forget that n is chosen such that n is more than mod x. N could be chosen any other number, correct? Any number more than that, any number more than mod x is fine. Okay, now when we have obtained this expression, we can now check what happens if n becomes very large. Okay, what can you say? We can say something that here denominator goes to 0, here also denominator goes to 0, and here numerator also becomes very large. Okay, very large. Okay, and then that means also with the negative sign this will also be small number. However, n also appears here, n square. So these terms actually give you confidence that okay, this part would go to 0, this part would go to 0, but here also I have a n square. So here we can observe that okay, here also I have n square term, okay, but there are some coefficient 1 over 2t here a. If I can say that this 1 over 2t is more than a, okay, or a is less than 1 over 2t, okay, then this part would dominate. So this decay of this numerator to 0 would actually lead everything go to 0. Okay, so this is the argument we are now going to put. If a is smaller than 1 over 2t, okay, then the right hand side, I mean this is some condition which we have not introduced earlier, remember? So because we have started with any particular capital T, okay, and a was just a parameter which appears in the assumption, okay. But here we are requiring one relation between a and 1 over 2t. But we would show that we can avoid, I mean for this step we actually require it, but for general case also we can get the same conclusion, but that would come later. First we finish this part. So a is less than 1 over 2t, then right hand side converges to 0 as n tends to infinity. Therefore this left hand side is equal to 0. Why? Because the left hand side does not depend on n. This is true for all possible n large. So you just take n tends to infinity, and then this goes to 0 for the special case where a is smaller than 1 over 2t. Okay, so that proves that this would be 0. But then it is yet incomplete proof. This is a proof only for a special case. Now let us talk about the general case. So if capital T is not less than 1 over 2a, then what we do, that because we don't have any control on a. Why? Because a is coming from the class of functions. Okay, we are looking for class of functions or the solutions, okay, such that the growth property is, you know, like k times less than equal or equals to k times e to the a n square, ax square. But t is a given problem, correct? Because 0 to t, we need to solve the equation for the interval times 0 to capital T. Now if capital T is too large, then we can actually subdivide capital T in small parts, T0, T1, T2, T3, etc. Tm, where Tm is equal to capital T. So when we subdivide capital T in these small parts, we divide it such a way that this every subinterval width is small enough such that that is less than 1 over 2a. So a is less than 1 over 2t, then t is less than 1 over 2a. But if you don't have, we actually have the subinterval. And for heat equation, we are now going to take these subintervals each one at a time. Okay, so now this is 0. So now we are going to, instead of capital T, we are going to take only T1 as our last final time interval, and then we are going to prove that okay, this is 0 everywhere till T1. And since we know that till T1 it is 0, we take that as my initial condition again, and then I've tried to write down that here. So, and then considering T2, T small t between capital T I minus 1 to capital T open I, okay, successively for I is equal to m to m minus 1. So this is like, either you start from 1 or m. So here if you do for m, that means you assume that it is 0 at I mean, like, for induction, so you have done it for till m minus 1, then you do for m. Otherwise you start from I is equal to 1, so like, 1 at a time. So for each this thing I you do separately. So thus we can prove that for any capital T positive real number, so this would be 0. So what we have obtained is that for a heat equation on infinite horizon, okay, so like 0 to capital T, and initial condition, if that is 0, initial condition is given in the way that okay, as limit this tends to 0, then that is 0. Okay, so then the solution must be 0. Solution must be the trivial solution. Okay, there is no non-trivial solution for that problem. Okay,